6.7 Empirical Formula. Distinguishing between empirical formula and molecular formula. Empirical formula is a formula that shows the simplest whole number ratio of the elements in a compound. Whereas a molecular formula is a formula that shows the element symbols and the exact number of each type of atom in a molecular compound. Here we have a table showing the empirical formula and the molecular formula for different structures. First, we have methanol, which has an empirical formula of CH2O and a molecular formula CH2O. Now, ethanoic acid is the next example. And notice that the empirical formula and the empirical formula for methanol and ethanoic acid are the same. But the molecular formulas are different. The empirical formula represents the simplest whole number ratio between these two. But it's not the actual number of elements. The actual number of elements is 2 carbon, 4 hydrogen, and 2 oxygen. The empirical formula and the molecular formula are related. They have the same ratio, and you can get the empirical formula by dividing this molecular formula by 2. When we do experiments in labs, we can find the empirical formula, and then we would need to find a way to determine the molecular formula to know the exact number of each type of atom in the molecular compound. Let's try an example. Determining a simple empirical formula. Find the empirical formula of a compound with a percentage composition of 35.4% sodium and the remainder nitrogen. Let's start with a convenient mass. Let's say that the mass of this sample is 100 grams. What we want to do since sodium takes up 35.4%, let's find out how much of the mass that would be. So 35% of 100 grams is 35.4 grams. The remainder is nitrogen. So if the complete sample is 100 grams and the sodium makes up 35.4 grams, then the amount of nitrogen is 64.6 grams. Now let's calculate the number of moles of each element. The number of moles of sodium is equal to the mass of sodium divided by the molar mass of sodium. We chose a 100 gram sample, so the mass of sodium is 35.4 grams. And the molecular mass of sodium from a periodic table is 22.99 grams per mole. So that gives us 1.54 moles of sodium. Let's do the same for nitrogen. We know there are 64. We'll find the mass of nitrogen divided by the molar mass of nitrogen. That's 64.6 grams divided by the molar mass, which is 14.01 grams per mole. And we see that we end up with 4.61 moles of nitrogen. In step 3, we want to determine the simplest ratio of the elements in the compound. So what we're going to do, since we know that there are 1.54 moles of sodium and 4.61 moles of nitrogen, we're going to divide the number of moles of each element by the smallest amount. So the smallest amount is the amount of sodium, which is 1.54 moles. And we're going to divide both of those amounts by 1.54. So we get the mole ratio of sodium as 1 to 2.98. This is showing a mole ratio of 1 to 3. If we know there is a mole ratio of 1 sodium to 3 nitrogen, then we can say that the empirical formula is NaN3. Remember, when we're writing formulas, we don't have to write the subscript 1, it's implied. So the molecular formula, or the empirical formula rather, is NaN3. Let's determine a more complex empirical formula. Determine the empirical formula of a compound that contains 69.9% iron and 30.1% oxygen by mass. In step 1, we're going to calculate the number of moles of each element, again choosing a simple 100-gram sample. So the number of moles of iron is equal to the mass of iron divided by the molar mass of iron. The mass of 69.9% of 100 grams is 69.9 grams of iron. And the molar mass of iron from the periodic table is 58.85 grams per mole. So that gives us 1.2516 moles of iron. Let's do the same this time for oxygen. We have the mass of oxygen divided by the molar mass of oxygen. In a 100-gram sample, 30.1% would be 30.1 grams of oxygen, and the molar mass of oxygen is 6.02 grams per mole. If we compute this, we end up with 1.8813 moles of oxygen. Step 2 is the same as it was in the previous example. We're going to divide the number of moles of each element by the smallest amount. So the number of moles of iron is 1.2516 moles, and the number of moles of oxygen is 1.8813 moles. So we'll divide both of these by the smaller amount, which is 1.2516. So we end up with a mole ratio of 1 iron to 1.5 oxygen. To convert this to the simplest whole number, we multiply both by 2, so we get 2 to 3. So initially, we had 1 to 1.5, but we multiplied these by 2 to get the empirical formula F2O3. Therefore, the empirical formula of the compound is Fe2O3. Let's determine the empirical formula with 3 elements. Determine the empirical formula of a compound that contains 52.2% carbon, 6.15% hydrogen, and 41.7% oxygen. Let's start by determining the number of moles of each element in a 100-gram sample. Again, choosing this 100-gram sample, which makes calculating the mass with these percentages really simple. So we'll start with the number of moles of carbon is equal to the mass of carbon divided by the molar mass of carbon. 52.2% is 52.2 grams out of 100 grams, and the molar mass of carbon is 12.01 grams per mole. That gives us 4.346 moles of carbon. Let's do the same for hydrogen. It's equal to the mass of hydrogen divided by the molar mass of hydrogen. 6.15% becomes 6.15 grams out of 100 grams. And the molar mass of hydrogen is 1.01 grams per mole. So we end up with 6.0891 moles of hydrogen. Let's do the same for oxygen. The mass of oxygen divided by the molar mass of oxygen. In 100 grams, 41% becomes 41.7 grams divided by the molar mass, which is 16.01, or 00 rather, grams per mole. Punch this in, and we get 2.6063 moles of oxygen. So that's 4.346 moles of carbon, 6.0891 moles of hydrogen, and 2.6063 moles of oxygen. Now we're going to do as we did in the previous examples, where we divide each of these by the smallest number of moles present. So the smallest number of moles is 2.063. Divide everything by 2.6063. And you'll see that we get 1 for oxygen, 1.67 for carbon, and 2.29 for hydrogen. Now we have to find the simplest whole number ratio, because right now as it stands, we have the formula C 1.67, H 2.29, and O 1. If we multiply each mole ratio in the subscripts by 3, we end up with C5H7O3. So basically you have to find the mathematical relationship that exists between these numbers and find out which number we need to multiply by to get the nearest whole number ratio for all three of these. And in this case, it's probably going to work by trial and error. And there aren't many numbers that you can multiply by or need to multiply by. So start by multiplying by 2, then by 3, then by 4, and see which number you need to multiply by to get the nearest whole number ratio. Please read over this section and try any practice problems as well as any LMS quizzes that are assigned.